simplistically between the velocity and y?
Well, we can.
Let's go back and look at this picture for a second and see if we can write, can we write a relationship that's going to connect what you just mentioned, Daniel, the y motion in the problem. Let me come back here and look in the book. This y position defined related to v.
We have a relationship between L dot and V.
Yeah, we have this
has
Pythagorean relationship, don't we? Yeah. Right. So we can take that Pythagorean relationship. Let's go ahead now and grab the Pythagorean relationship, which says that we have y, we have b, and we have L. And so L squared equals b squared plus y squared. Right? So differentiate this implicitly. So 2L L dot equals 2y y dot.
B's constant.
And L dot is V, is it not?
Yes. Wasn't it?
Is it positive or negative?
2L dot equals V.
L dot wasn't V.
No, we came up with.
S dot was V. Could you?
So anyway, let's keep going here for a second.
2L dot equals negative V.
You're not going to use the constrained motion equation to write them?
Okay. So what I want us to investigate for just a second here is how's L dot relate to Y dot? What's L dot?
Oh, I see.
L dot is
Angle
S dot over 2.
Here's where this thing comes down, spools up onto this drum, right? Spools up onto the drum, and this thing is moving this way with some V. Where is V in here?
No,
Well, don't we have the constrained motion equation?
L equals negative V over 2, right?
Isn't-
L dot.
Isn't V negative L dot? Or L dot negative V?
Well, we have the equation zero equals
Because
2.
doesn't this length contract? Doesn't this length contract as that thing moves? So am I correct on that? Isn't L dot equal to the negative of the V reading?
But there's the length equation we came up with for the chord. 2L plus S equals the length of the chord.
Okay,
So if you divide your V by 2, you should be straight.
let's put a question mark up there on that. Conjecture. So we wrote a length equation where this is a fixed length. And then we said it was made up of 2 pieces of L plus some amount on the drum plus some constant. Differentiating that, so we get S dot equals minus 2L dot. S dot is V. That's equal to V. So L dot is equal to negative V over 2. Not that. Do you see how my thinking here is wrong? What caused that wrong thinking?
Your picture doesn't include the other half of it. So
It doesn't include the other half of that, which is another piece of L over there. It's the combination. See, that pulley is letting some of this length get drawn over there, isn't it? Does that make sense to you?
Yes.
Okay. So sometimes you don't see these things until you fiddle with them. But then if you go back and rely on the mathematics, as I keep saying, and you get your mathematics right, you can see your relationships. Okay, now, is that enough probably to get you going? Okay. So you folks can take that information then and see if you can wrap it up and come up with the answer shown in the book. Okay, we have a few minutes left. Let's go ahead and see if we can get let's come back over to the work energy stuff. Unless there's some pressing other problem that's puzzling everyone.
I don't know if everyone's been puzzling this one, but 245, page 138.
Oh, yeah.
Yes.
It's unanimous. 235, 148,
Page 138.
138, excuse me.
Yeah, the two blocks with the rollers
Oh,
connected
yes,
with the
that
rigid rod thing.
Oh, number 45 you said?
Yes.
I'm not going to do that. Okay. This lays, first of all, this one lays on a horizontal table. Notice I underlined that. Horizontal plane, so MG is not part of it. Okay, so MG is not part of it. That's one thing. Okay. That took care of half of you.
I was able to get the right answers with using MG.
Well,
Yeah, I got the exact answers in the book.
That's probably just.
Pure willpower.
I think because
Some
energy is a
people are-
constant in this case, it doesn't actually affect the p-force acceleration, so it doesn't.
Yeah, I think that's exactly what's
so
probably
it
happening.
would divide out somewhere.
Because see, yeah, here's the driver over here. That's the reason probably MG didn't
Well,
matter.
but the weight on block B should be helping it come down its incline if you look at it from the side,
Yeah,
which
I
it's
think that's
not.
the side.
But it
Yeah.
seems like if you included
I know.
weight and it was a
That does. Maybe there was a little magic in the work there. Okay.
Well,
And sort of you say, obviously, it's obvious that, and then write these answers down. That kind of thing. Okay.
For observation.
It can be shown that.
Yeah. I don't know if you folks have experienced that. Well, I'm sure you'll have. I know you have. It'll say in a calculus book or a physics book or an engineering text, it'll say, it can be shown that, and then blah, 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 here's your equation, and by several pages later of hand calculations, you might be able to demonstrate that, or it's intuitively obvious that.
I've done that on a test where we discussed this previously, and thus I will present it here without proof.
Yes, right. Didn't work, did it?
Well, it wasn't.
Oh, okay. What you want to do on this problem is write law of cosines. So you know, what I did in helping a couple people with this one is I labeled this distance B. Now, one thing you want to be careful with here, tell you what I'm going to do just for clarity, I'm going to write it up here on the board.
Why do we need to know those distances?
Now,
You'll find out here.
that'll be, I think that'll be clear once I do this.
to apply the law of cosine to the triangle. Take the derivatives to be able to relate all their accelerations and velocities.
Here's your P-force.
Otherwise, you have
You have this rod that's in tension.
Know that angle though.
Notice that you've been seeing me do this consistently. I break these like cables or rods apart, and I show the equilibrium compatibility. What's really nice about this, and you probably saw this in strength of materials to make it clear, is this indicates real clearly that rod's in tension. Or at least I'm assuming it's in tension by drawing these arrows like this and then writing the equations that way. Okay. I could work the problem out, and I could reverse the P-force and actually put that rod in compression, and the mathematics, all the pages of mathematics would still be valid. All I'd have to do is assign a negative number to this P, and the mathematics would carry out, and the tension would turn out to be opposite to what you see here. You get a negative result. So as long as you draw a good free body diagram, write all your equations consistently with that, then it'll all work out, shake out. Now, I think they gave us 150 degrees here on this thing.
Yeah.
And this is called body B. If there's a tension here, folks, that is transverse to the motion's this way. If there's tension with a component that's transverse to the motion, that means there has to be, if you're not going to allow motion in that transverse direction, then there has to be a resisting force to that. And so that means there has to be a normal force exerted by the sidewall. If there was friction in this problem, that normal force would be what would be creating that friction effect. Similarly, down below, there's a transverse force upward due to the tension. So that means there's going to have to be a downward normal force here on body A. Now, here's a place where you can make a mistake in this problem. If you define the distance here to this body as B, keep in mind that that's the direction from this non-moving reference down here. That's the direction of positive B. B dot is physically going to be what? Negative, given the loading. B dot will be negative, the velocity. Whereas over here, you define this distance as A, again measured from a non-moving reference, and the motion at that point is positive, then A dot is going to be positive. And sometimes, just for to keep you safe about doing your calculations, positive B dot would be that way, positive B double dot would be that way. This would be the positive sense for all those kinematic relationships there. Positive sense here, A dot, this would be positive for A dot, and positive for A double dot. Okay, if you write law of cosines now, the fixed length L, A squared plus B squared minus 2AB cosine the 150. Here's a place, Heather, I think we had fun with that, or no, Julie.
Yeah.
We had fun with this. The cosine of 150 degrees, think unit circle, folks. Cosine of 150 is negative rad 3 over 2. So that makes this become positive. AB square root of 3. You have to differentiate this thing with respect to time twice. It gets messy. And track your work very carefully. And it does get messy though. Track your work carefully, and then you can work it on out from there. Okay. That might help a little bit. Okay. Any other questions from homework? Okay, I've got about maybe 5-8 minutes or so to at least introduce the concept of potential energy with you. And in the interest of time, I'm going to show you something here in the book, and then I'll put a couple things up on the board. We have potential is stored energy. Potential is stored energy. The other day we talked about the spring. If the spring is distorted from its either into tension or compression, it's got energy stored into it. It wants to release that and give it up and return to its unstretched length. Okay? So whether it's in compression or tension, it wants to return to its unstretched length. Similarly, with a mass and a gravitational field, if we move the mass, and this goes back to Newton's law of attraction, if we move the mass away from the attractive mass, the mass it's being attracted to, if we move them apart, then what happens is we are storing more energy into that moving, the mass we're moving, we're storing energy into it. If we let it go, so it can come back and actually move towards the other mass, then it's going to give up that potential and speed up as it accelerates, because there's an unbalanced force then. You're sitting here in your chair statically. If all of a sudden the chair disappeared, you would be accelerating. What you've got going on there is you've got a normal force pushing up against you that keeps you stationary, to you balanced with your mg downward. We define gravitational potential energy, as they've done here in the book, as mgh. Keep that in mind. We, in a similar sense, we define for a linear spring elastic potential energy as 1/2 kx squared, where x is what? What's x physically?
Distance from equilibrium.
Distance from the unstretched length. So those are definitions that we're going to work with. And there's some wording here that you want to be real clear on. Right up here I underlined it. The work which is done on the spring to deform it is stored in the spring and is called the elastic potential energy. So it's the work done to the spring. The work done to the spring is called elastic potential energy. Back over here on the gravitational potential energy, the gravitational potential energy is defined as the work mgh, work, force times distance, done against the gravitational field to elevate the particle a distance h above some reference plane. We call that the datum. We call that the datum. So let me put a couple notes up on the board here, and that'll be just about all the time we have today. We set up a gravitational reference level. We have a body at some altitude, let's call it h1. It's carrying some gravitational potential. By definition, we use capital V for this, gravitational potential, V sub g. It's carrying mgh1. If we move it away, further away, to some h2, it's now carrying mgh2, measured from the datum. The change in gravitational potential is equal to Vg at 2 minus Vg at 1. So we get mg h2 minus h1. Notice that this is the negative of the work done by mg. This is the negative of the work done by mg, which I talked about at the beginning of the session. So if we had our equation the way we had it the other day and earlier today, we would have a term sitting over here. We'd have work due to various forces other than gravity, and we would have this minus mg h2 minus h1 over here. And if we move that over to the other side of the equation, it becomes the change in potential. Becomes the change in potential. So we get the work done by other forces is equal to the change in kinetic energy plus the change in gravitational potential that okay? And how much time do I have left? No time? Okay, I got no time left. Just to close this off, we're going to put that elastic potential energy there. This is the way we're usually going to be running this equation. Okay? So don't forget to show up at 4 o'clock next Monday at the Math Resource Center for that midterm. See ya.